The cosmos is a realm of wonders and terrors, home to galaxies and planets whose secrets are both mesmerizing and chilling. Far from our sun's nurturing glow exist worlds so extreme they defy imagination. Picture planets scoured by sideways rain of molten glass, shrouded in eternal night, or seething with global oceans of lava. These are not the placid orbs of our dreams. They are the universe's most hostile planets, where environments are so brutal that known life would be instantly annihilated. Consider HD 189733b, a hot Jupiter, infamous for its weather. Supersonic winds whip scorching clouds into a relentless, horizontal rain of molten glass.
The atmosphere of HD 189733b is scorching and turbulent, with temperatures reaching over 1,000 degrees Celsius, 1,832 degrees Fahrenheit, due to the planet's close orbit and intense exposure to stellar radiation. Within this extreme environment, silicate particles form and exist in a molten, vaporized state. The conditions on HD 189733b present a staggering contrast to those on Earth, particularly in its wind speeds. While the most powerful hurricanes on Earth have winds of about 250 kilometers per hour, 155 miles per hour, the winds on this exoplanet howl at speeds exceeding 7,000 kilometers per hour, 4,350 miles per hour, nearly 20 times faster. At such velocity, the air could traverse the continental United States from coast to coast in under 2 hours, illustrating the sheer magnitude of the atmospheric forces at work. The extraordinary winds of HD 189733b are driven by the planet's close orbit, which creates extreme temperature differences between its hot and cool sides. This disparity forces air to rush from the hot to the cool regions with a violence that defies earthly analogs. On this world, wind is a defining force, directly responsible for the surreal phenomenon of glass rain. Unlike Earth's life-giving rain, the precipitation on HD 189733b is a hostile barrage. Molten silicate particles in the upper atmosphere are swept up by the winds, cooling into solid shards of glass that do not simply fall, but are launched horizontally at speeds up to 7,000 kilometers per hour. This relentless, high-velocity bombardment shapes the planet's landscape in ways that are almost impossible to comprehend. The surface of HD 189733b, constantly bombarded by high-velocity glass, is likely left rugged and scarred. Over geological time, this relentless assault could build vast reflective dunes of glass, creating a landscape that glitters ominously under its nearby star. This glass rain does more than just shape the terrain. It defines the planet's very energy dynamics. The combined heat from the star and the kinetic energy from the falling glass create an atmosphere in perpetual, violent flux. Such extreme conditions undoubtedly prevent the existence of liquid water, a fundamental requirement for life as we know it, making the possibility of habitable zones on HD 189733b non-existent. In stark contrast, the exoplanet TRES 2b, located about 750 light-years away, holds the title of the darkest known planet. It reflects less than 1% of the sunlight that hits it, making it darker than coal. The cause of TRES 2b's profound blackness lies in its unique atmospheric composition, which is rich in light-absorbing chemicals like vaporized sodium, potassium, and titanium oxide. However, the atmospheric conditions on TRES 2b prevent this reflection. Instead, its atmosphere absorbs almost all incoming sunlight, trapping it as heat. This process is so efficient that it prevents light from being reflected back into space, accounting for the planet's profound darkness. Another factor contributing to the darkness of TRES 2b is the potential presence of unknown, light-absorbing compounds. Scientists speculate that these materials could be responsible for the exceptional level of absorption, though their exact nature remains a key subject of ongoing research. The planet's searing temperatures, which can reach up to 1,000 degrees Celsius, 1,832 degrees Fahrenheit, are also a significant factor. This intense heat sustains the chemical reactions that lead to the absorption, rather than the reflection, of light. A prevailing theory suggests the atmosphere is rich in vaporized sodium and potassium, both of which are potent absorbers of visible light. In the high-temperature environment of TRES-2b, these elements prevent sunlight from being reflected. Additionally, while titanium oxide can be reflective in other planetary atmospheres, it is hypothesized that the extreme conditions on TRES-2b cause it to contribute to light absorption instead, further deepening the planet's mysterious black appearance. Researchers theorize that beyond known substances, TRES-2b's atmosphere may harbor unidentified compounds that further enhance its light-absorbing capabilities. These unknown elements are considered crucial to the planet's profound darkness, potentially representing novel chemical processes that only occur under the extreme temperatures and pressures found on such exotic worlds. Shifting from profound darkness to intense light, the exoplanet Kepler-70b exists in a realm of extreme heat that challenges our understanding of planetary climates. Orbiting incredibly close to its host star, Kepler-70b endures temperatures that far exceed those of most known planets. Its surface temperatures soar to a staggering range of 6,700 degrees Celsius, 12,092 degrees Fahrenheit, to 7,300 degrees Celsius, 13,172 degrees Fahrenheit, ranking it among the hottest planets ever discovered. These conditions resemble the outer layers of a star more than a typical planetary atmosphere. This extraordinary heat is a direct result of its tight orbit around the star Kepler-70, which bombards the planet with extreme levels of stellar radiation. This proximity heats the world to the point where metals and rock are vaporized, creating an environment that is not only inhospitable, but almost inconceivable in its ferocity. The concept of day and night is irrelevant on Kepler-70b, resulting in nearly uniform, searing temperatures across its entire surface that push matter to the very brink of becoming plasma. The close proximity of Kepler-70b to its host star, Kepler-70, forges a surface environment beyond terrestrial comparison. The intense stellar radiation from this tight orbit directly creates physical characteristics that defy imagination. The heat is so extreme that metals and rocks do not merely melt, they vaporize. This results in a landscape in constant flux, with surfaces that may be molten or partially vaporized, potentially featuring pools of liquid metals and silicates that create a shimmering, reflective vista utterly unlike Earth. Furthermore, the powerful gravitational forces from its close orbit subject Kepler-70b to significant tidal stresses. These forces deform the planet, likely triggering intense volcanic activity and creating unusual geological formations. This makes Kepler-70b a dynamic and ever-changing world, where the very ground is as transient and unstable as its atmosphere. The planet's extreme conditions stand as a testament to the diverse and severe environments that can exist in the cosmos. The close proximity of Kepler-70b to its host star, Kepler-70, forges a surface environment beyond terrestrial comparison. The intense stellar radiation from this tight orbit directly creates physical characteristics that defy imagination. The heat is so extreme that metals and rocks do not merely melt, they vaporize. This results in a landscape in constant flux, with surfaces that may be molten or partially vaporized, potentially featuring pools of liquid metals and silicates that create a shimmering, reflective vista utterly unlike Earth. Furthermore, the powerful gravitational forces from its close orbit subject Kepler-70b to significant tidal stresses. These forces deform the planet, likely triggering intense volcanic activity and creating unusual geological formations. This makes Kepler-70b a dynamic and ever-changing world, where the very ground is as transient and unstable as its atmosphere. The planet's extreme conditions stand as a testament to the diverse and severe environments that can exist in the cosmos. The phenomenon of burning ice on GJ1214b arises from the planet's dense atmosphere and the incredible pressures within its potential oceans. Under this immense atmospheric pressure, water is forced into a state known as a supercritical fluid, which blurs the distinction between liquid and gas. In this exotic phase, water can dissolve materials like a liquid, while also expanding to fill space like a gas. It is not frozen ice, nor is it a flame, but the extreme conditions lead to this evocative description. The temperatures on GJ1214b, while not the most extreme known, are high enough to prevent water from existing as a familiar liquid on the surface, locking it instead into this supercritical state. This creates an environment where water behaves in ways completely alien to Earth. The pressure on GJ1214b presents a staggering contrast to even the deepest parts of Earth's oceans. In the Mariana Trench, pressure reaches about 1,086 bars, 15,750 pounds per square inch, a force often compared to the weight of an elephant on a postage stamp. On GJ1214b, however, the atmospheric pressure is estimated to be thousands of times greater, pushing the concept of pressure into an entirely new and extreme realm. This immense pressure is a result of the planet's substantial mass, high density, and a thick atmosphere likely laden with heavy molecules. Under these extreme conditions, water and other substances undergo dramatic transformations, entering exotic phases like the supercritical fluid state, where the conventional boundaries between gas and liquid completely break down. However, studying GJ1214b and its intriguing characteristics presents a unique set of scientific challenges. These stem from both technological limitations and the inherent difficulty of interpreting data from such a remote world. A primary hurdle is the vast distance itself. Located approximately 40 light-years from Earth, observing GJ1214b requires advanced telescopes with exceptionally sensitive instruments to analyze its atmosphere and temperature. Another significant challenge is the resolution of our current technology. Despite major advancements, our instruments still struggle to detect the finer details of exoplanetary atmospheres, such as identifying specific molecules or understanding dynamic weather patterns. This task is compounded by the host star's overwhelming brightness, which often obscures the faint signals from the planet, making it difficult to isolate the specific characteristics of the light GJ121. The interpretation of data from GJ1214b is further complicated by our limited understanding of how matter behaves under its extreme pressures and temperatures, such as in the supercritical fluid state. Scientists rely on theoretical models and laboratory experiments to simulate these conditions, but these cannot perfectly replicate the complex environment of a distant exoplanet. Consequently, there is a continuous scientific effort to refine these models and develop new techniques to better decipher the observations of GJ1214b. In a different extreme, WASP-12b, an exoplanet located about 600 light-years away, has been dubbed a doomed planet. This gas giant, similar in size to Jupiter, is in a perilously close orbit around its host star, WASP-12, and is being slowly consumed by it. This fate is a stark illustration of the destructive forces that can shape planetary life cycles. The primary reason for WASP-12b's doomed status is its extreme proximity to its star. This results in powerful gravitational forces that have tidally locked the planet. One side permanently faces the star, while the other is in endless darkness. The star-facing hemisphere experiences scorching temperatures over 2,500 degrees Celsius, 4,532 degrees Fahrenheit, causing the planet's atmosphere to be stripped away into space. The intense gravity has also distorted WASP-12b into an elongated, egg-like shape, a dramatic departure from the typical spherical form of planets. This dramatic deformation is a direct result of the star's overwhelming gravitational influence. Observations indicate that WASP-12b is losing mass at an immense rate of approximately 189 quadrillion tons per year. This is caused by the star's intense heat and gravity stripping away the planet's outer layers, a process known as atmospheric escape. Scientists predict that within a short astronomical time frame, possibly as little as 10 million years, WASP-12b will be completely devoured by its host star. This inevitable consumption solidifies its status as a doomed planet and underscores the dynamic, often violent nature of planetary systems. Studying WASP-12b's demise provides crucial insight into the life cycle of hot Jupiters and serves as a powerful reminder of the forces that govern our universe. Observations of WASP-12b's death spiral offer a fascinating and ominous window into extreme celestial mechanics. By using powerful telescopes and space-based observatories, astronomers have gathered critical data on this process. The most compelling evidence comes from the detection of a vast cloud of material being pulled from the planet toward the star, a direct consequence of WASP-12b's close orbit and the immense gravitational forces tearing it apart. This stream of material forms an extended atmosphere, or a bridge of gas, stretching from WASP-12b toward its star, which slowly siphons off the planet's substance. Spectroscopic analysis has been instrumental in studying this process. This technique, which determines composition by analyzing light, has allowed astronomers to identify various gases in the stream, including hydrogen, helium, and even heavier elements that are actively being stripped from the planet's atmosphere and accreted by the star. The significant rate of mass loss has caused WASP-12b to become distorted and elongated due to the immense tidal forces from its star. This distortion disrupts the planet's gravitational equilibrium and, in a feedback loop, accelerates the atmospheric escape process, hastening its demise. As WASP-12b loses mass, vast quantities of gas are stripped from its atmosphere. This includes not only hydrogen and helium, but also heavier elements, drastically altering the atmospheric composition. This stripping leads to a decrease in atmospheric pressure, upsetting the balance with the vacuum of space. Meanwhile, the intense stellar heat causes the remaining atmosphere to expand, making it escape more readily and thinning it further. A thinner atmosphere offers less protection from stellar radiation, leading to even higher surface temperatures and altered surface chemistry. Furthermore, the powerful tidal forces exert internal stress on WASP-12b, heating its interior. This can induce volcanic activity and other geological processes that reshape the planet's surface over time, creating new features or eroding existing ones. The study of WASP-12b's death spiral provides a window into its ultimate fate and has broader implications for understanding planetary evolution. These observations have challenged previous assumptions about orbital stability and the factors leading to a planet's destruction. Moving from the captivating fate of WASP-12b, the enigmatic case of HD 106906b presents a stark contrast. With its peculiar and disrupted orbit, defying conventional planetary systems. Located about 300 light-years from Earth, HD 106906b presents a curious astronomical case due to its exceptionally distant and elliptical orbit. This exoplanet resides at a staggering distance of over 650 times the Earth-Sun separation, placing it in a region where standard models of planet formation and orbital dynamics fail to provide clear explanations. The disrupted orbit of HD 106906b raises intriguing questions about its past. One leading theory proposes that its current path resulted from powerful gravitational interactions, perhaps with other planets in the system or a passing star, which violently altered its trajectory without ejecting it completely. Another fascinating aspect is the planet's orbital inclination. Observations show its orbit is significantly tilted relative to the main plane of its solar system, suggesting a dynamic and possibly turbulent history involving interactions that are not yet fully understood. The unusual orbit of HD 106906b not only captivates scientific curiosity, but also poses a significant challenge to our existing theories of how planetary systems form and evolve. Traditional planetary formation models are centered on the protoplanetary disk, a rotating disk of gas and dust around a young star where planets coalesce and settle into orbits aligned with the disk's plane, much like our own solar system. The extraordinary orbit of HD 106906b, however, with its immense distance from its host star and its significantly inclined path, challenges this concept and suggests that other, more dynamic processes are at work. A key puzzle posed by HD 106906b is understanding how a planet can attain such a wide and tilted orbit, as traditional accretion models cannot easily account for it. This discrepancy points to the involvement of gravitational interactions beyond simple disk dynamics. Leading theories propose that disturbances from other massive bodies within the system, or even a close encounter with a passing star, could have violently perturbed the planet's trajectory. Such scenarios imply that the early history of this solar system was far more chaotic than once assumed. Furthermore, the existence of HD 106906b challenges our understanding of how stable orbits are achieved. Its current path suggests a complex migratory history, potentially involving dramatic events like planet-planet scattering, or even capture from a different star system entirely. Such chaotic processes could explain the vast diversity of exoplanetary systems observed by astronomers, which far exceed the orderly configuration of our own solar system. Delving deeper into the mystery of HD 106906b, its extraordinary orbit points to an origin story shaped by dramatic celestial dynamics. One compelling theory suggests that HD 106906b's path was sculpted by gravitational interactions with an unseen companion in the system, such as another massive planet or a brown dwarf. Early in the system's history, these interactions could have violently ejected HD 106906b outward. This scenario required a precise balance of forces, perturbing the planet just enough to strand it in a wide, inclined orbit, without ejecting it from the system entirely. An alternative hypothesis proposes that a close encounter with a passing star disrupted the young system. Such an event would be more likely in a dense star cluster. The gravitational pull from this interloper could have significantly altered HD 106906b's velocity and direction, setting it on the unusual and distant course we observe today. Furthermore, the early dynamical evolution of the HD 106906 system may hold the key to its planet's strange orbit. A process known as planet-planet scattering, where gravitational interactions between young planets violently sling them into new paths, could account for HD 106906b's current location. This chaotic mechanism often ejects planets into wider, more eccentric orbits, and could potentially explain the high inclination observed. Shifting from orbital mysteries to extreme weather, the exoplanet Korat 7b, located 489 light-years away, exhibits the fascinating phenomenon of rock showers. This world's extraordinary conditions are a direct result of its extreme proximity to its host star, orbiting 23 times closer than Mercury does to our Sun. This results in dayside surface temperatures soaring to approximately 2,500 degrees Celsius, 4,532 degrees Fahrenheit. At such incredible heat, surface rock doesn't just melt, it vaporizes, creating an atmosphere of mineral gases. On the scorching day side, rock vaporizes and is carried by atmospheric winds to the much cooler night side. There, temperatures plummet, causing the rock vapor to condense into particles that precipitate as showers of rock. This continuous cycle of vaporization and condensation is a fundamental feature of Korat 7b's climate, driven entirely by the severe temperature differential. Additionally, strong gravitational forces from the star distort the planet's shape, which in turn influences how these rock vapors circulate through the atmosphere. The powerful tidal forces acting on Korat 7b not only distort its shape, but also generate significant internal heat, adding further complexity to its already extreme weather patterns. The planet's unique phenomena, where dayside temperatures of 2,500 degrees Celsius vaporize rock, and nightside cold condenses it into rock rain, create a natural laboratory for studying processes impossible to observe in our solar system. This violent cycle of vaporization and condensation provides invaluable insight into how minerals and rocks behave under extreme conditions. Understanding these processes helps scientists refine models of planetary formation and evolution, shedding light on the early history of Earth itself, including the development of its crust and atmosphere. Furthermore, studying Korat 7b's atmospheric dynamics allows researchers to explore the effects of severe temperature gradients on weather patterns, improving our understanding of climate across a vast range of planetary environments. The conditions on Korat 7b challenge fundamental theories about habitability and the prerequisites for life. By expanding our knowledge of how planets evolve under diverse extremes, we can better assess the potential for life elsewhere and refine the search for exoplanets by identifying which characteristics signal a world worthy of further study. Shifting focus from one extreme to another, scientists are captivated by 55 Cancri e, a super-Earth exoplanet located about 40 light-years away. This planet is theorized to have a carbon-rich composition, which under immense pressure and heat could form a surface rich in diamonds. This extraordinary hypothesis is grounded in the planet's unique carbon-rich composition and the crushing pressures it experiences. Unlike Earth's silicate-based crust, 55 Cancri e is believed to be composed primarily of carbon. The planet's immense internal heat and gravitational pressure are the driving forces that transform this carbon into diamond. The process begins deep within the planet, where temperatures are sufficient to melt carbon. Under the overwhelming pressure from the planet's own mass, this molten carbon then crystallizes into diamond. While analogous to diamond formation on Earth, which occurs about 150 kilometers underground over billions of years, the process on 55 Cancri e is vastly more intense and widespread, potentially creating a thick layer of diamond at the surface. This theory is strongly supported by observational data. The planet's surprisingly high density indicates a composition of heavy elements, ruling out light gases like hydrogen and helium. Furthermore, its host star is known to be carbon-rich, providing the raw material. Together, this evidence leads scientists to conclude that 55 Cancri E could truly be a diamond world. The potential existence of such planets offers profound insights into the diverse and often unexpected outcomes of planetary formation throughout the universe. This discovery highlights the vast spectrum of conditions under which planets can form, resulting in an extraordinary variety of compositions and characteristics. A world like 55 Cancri E, potentially rich in diamonds, demonstrates that the cosmos is filled with planets that are not only alien to Earth but also to one another, underscoring the remarkable diversity of planetary systems. This diversity is primarily dictated by the raw materials available in the planet-forming region around a young star. In the case of 55 Cancri E, a high concentration of carbon relative to oxygen suggests its formation region was abundant in carbon-based compounds. This stands in stark contrast to Earth, which formed in a region richer in silicon and oxygen, resulting in a rocky silicate planet. The emergence of a diamond planet points to a protoplanetary disk with a unique chemical signature, emphasizing how the environment of a stellar nursery fundamentally shapes a planet's identity. Furthermore, the transformation of these materials under extreme pressure and heat, forming diamonds, offers critical clues about the internal processes and thermal dynamics of distant worlds. It indicates that some planets operate with internal heat and pressure mechanisms far different from Earth's, opening new avenues for research in planetary geophysics and chemistry. Studying the formation of planets with surfaces of valuable materials also deepens our understanding of the life cycle of stars and the planetary systems they birth. This diversity hints at the vastly different evolutionary paths planetary systems can take over billions of years. A carbon-rich world like 55 Cancri E would evolve under a completely different set of geological and atmospheric processes compared to a water-rich world or a gas giant, directly affecting its surface conditions and potential for hosting any form of complex matter. In a different display of cosmic grandeur, the rings of exoplanet J1407b represent a spectacular phenomenon in exoplanetary science. This ring system is not just vast but of an immense scale, utterly dwarfing any found in our solar system. To grasp its size, imagine Saturn's magnificent rings. The rings of J1407b are so extensive that they could envelop Saturn's entire ring system over 200 times. Spanning nearly 90 million kilometers, about 56 million miles, in diameter, they offer a stunning illustration of the incredible variety present in the universe. The discovery of these rings provides a fascinating window into planetary formation and ring dynamics. They are likely composed of ice, rock particles, and even embedded moonlets, small bodies that orbit within the rings, similar to Saturn's shepherd moons. Their sheer scale suggests they could be the aftermath of a colossal collision or a snapshot of moon formation in its early stages, shedding light on processes that may have shaped our own solar system, but on a vastly grander scale. Drawing a parallel from our own solar system, Saturn's rings demonstrate how moons can form from a planet's ring material. Ice and rock particles within the rings interact and coalesce under gravity, forming moonlets that may eventually become full-fledged moons. Given that the rings of J1407b are far more massive and extensive than Saturn's, it is highly plausible that similar processes of accretion and moonlet formation are occurring on a much grander scale. The theory suggests that as particles within J1407b's rings collide and stick together, they gradually accumulate into larger objects. These could eventually gain enough mass to clear their orbital paths, a critical step in becoming proper moons. Studying this process would offer profound insights into the formation of moons and small bodies, revealing the conditions, timescales, and dynamics involved in shaping a planetary system. Shifting focus from a world of formation to one of deep freeze, Ogle 2005 BLG 390LB is categorized as an iceball planet due to its extremely cold surface and distant orbit, ranking it among the chilliest exoplanets known. Located about 21,500 light-years away in Sagittarius, this remote world orbits its star at a distance far greater than Earth's from the Sun, receiving minimal stellar warmth. The term iceball is apt because its surface temperature is estimated to be around -220 degrees Celsius, -364 degrees Fahrenheit. This profound cold means any water exists as permanent, planet-wide ice. This categorization is based on its thermal characteristics and environment. Unlike ice giants like Uranus and Neptune, which have thick atmospheres of hydrogen and helium, an iceball planet like OGLE 2005 BLG 390LB is thought to be a solid, terrestrial body with a surface dominated by frozen ices. The extreme cold on OGLE 2005 BLG 390LB is a direct result of its distant orbit, which prevents it from receiving enough stellar energy to heat its surface. This classification of iceball planet highlights the remarkable diversity of planetary environments in the universe and challenges our understanding of habitability. While its frigid conditions seem inhospitable to life as we know it, studying such worlds helps scientists define the outer limits of planetary climates and the behavior of water in all its forms across the cosmos. In planetary science, temperature is a primary factor in determining atmospheric composition. On a planet as cold as OGLE 2005, BLG 390 LB, volatile compounds that are gaseous on warmer worlds, like water vapor, carbon dioxide, and methane, would freeze out of the atmosphere and settle on the surface as ice or snow. This process, known as atmospheric freeze-out, drastically reduces the thickness and density of the atmosphere, as very few gases remain in a vaporous state. The consequent lack of a substantial atmosphere means that any minuscule heat from its star or from the planet's own interior cannot be trapped effectively, creating a feedback loop that perpetuates the deep freeze. This stands in stark contrast to planets with thick atmospheres, where greenhouse gases can retain heat and maintain warmer temperatures even far from their star. Ultimately, the severe temperature and tenuous atmospheric conditions on OGLE 2005 BLG 390LB offer clear insights into its capacity to host life, indicating an environment that is profoundly challenging for biological processes as we understand them. The absence of a substantial atmosphere and the extreme cold make the existence of liquid surface water, a key ingredient for life on Earth, highly unlikely. However, these very conditions raise intriguing questions about the potential for life in extreme environments, pushing the boundaries of our understanding of habitability and the possibilities of extremophiles. Studying distant cold worlds like OGLE 2005b, LG 390LB, located thousands of light-years away, requires advanced astronomical techniques. Scientists rely on a combination of innovative observational methods and theoretical models to uncover the secrets of such remote and faint objects. A key method in the discovery and study of OGLE 2005 BLG 390LB is gravitational microlensing. This phenomenon occurs when the gravity of a star or planet, the lens, bends and magnifies the light from a more distant background star, the source, as they align from our viewpoint. This temporary brightening can reveal the presence of orbiting planets, providing data on their mass and orbital distance. Gravitational microlensing is uniquely powerful for detecting exoplanets that are too distant, faint, or far from their star for other methods. It does not rely on the planet's own light, but on its gravitational influence on light from an unrelated star, making it ideal for finding cold, low-mass worlds like OGLE 2005, BLG 390LB. In addition to this technique, scientists use sophisticated computer models and simulations to predict and interpret the conditions on such enigmatic planets. By inputting known physical characteristics, such as mass, orbital distance, and period, into these models, scientists can estimate the planet's atmospheric composition, surface conditions, and potential for hosting water or ice. This process allows astronomers to infer properties like temperature and whether the planet has a solid surface. Telescopes with sensitive instruments, both on Earth and in space, are vital for following up on microlensing discoveries. They provide additional data on the star system, helping to refine measurements and confirm the planet's existence. Although directly observing the atmosphere or surface of such a distant world remains challenging, combining these techniques offers valuable insights into its nature. Kelt 9b's status as the hottest known exoplanet stems from a combination of extreme factors. Located about 670 light-years away in Cygnus, KELT 9b orbits its host star, KELT 9, at an astonishingly close distance, completing an orbit every 1.5 Earth days. A primary factor is the star itself, which is nearly twice as hot as our Sun, making it one of the hottest stars known to host a planet. This incredibly tight orbit places KELT 9b in an intense stellar environment, where it is bombarded by a colossal amount of radiation. The combination of the star's immense heat and the planet's proximity means KELT 9b is subjected to thousands of times more radiation than any planet in our solar system receives from the Sun. This exposure heats its atmosphere to over 4,300 degrees Celsius, 7,800 degrees Fahrenheit, a temperature exceeding that of many stars and far above the melting point of most known materials. These extreme conditions lead to exotic atmospheric physics and chemistry, including the presence of vaporized metals and the breakdown of molecular hydrogen, which is a staple of other gas giants. Another key factor is the absence of a reflective atmosphere. While some planets can moderate their temperature by reflecting starlight, the intense heat on KELT 9b likely prevents the formation of reflective clouds or ice, causing the planet to absorb nearly all incoming radiation. Furthermore, the planet is tidally locked, with one hemisphere permanently facing the star. While powerful winds may attempt to redistribute some heat, the day side of KELT 9b remains eternally infernal, showcasing the most severe conditions known to exist on an exoplanet. For the hottest known exoplanet, KELT 9b, future observations are focused on probing its extraordinary atmosphere and the severe conditions created by its close orbit to the host star, KELT 9. Astronomers plan to use next-generation space and ground-based telescopes to explore this world in unprecedented detail. A primary objective is to conduct a deeper analysis of KELT 9b's atmospheric composition. This involves identifying exotic molecules and elements that can exist as vapors at its extreme temperatures, such as iron and titanium, and potentially discovering species that are unknown in cooler environments. Another key area of study is the planet's atmospheric dynamics and weather patterns. Scientists are keen to understand how heat is transported from the scorching day side to the cooler night side, which could reveal extreme weather phenomena unlike anything in our solar system. Advanced observatories like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are poised to be instrumental in these efforts. The JWST's unparalleled infrared sensitivity will detect KELT-9b's thermal emission, providing detailed data on its temperature distribution and chemical makeup. The ELT, with its massive mirror, will offer exceptional resolution, allowing for more precise study of the planet's atmospheric chemistry. Furthermore, future research will aim to characterize KELT-9b's magnetic field and its interaction with the powerful stellar wind from KELT-9. The highly eccentric orbit of HD 8606b, a gas giant located 190 light-years away in Ursa Major, is the direct cause of its extreme seasonal changes. Unlike the near-circular paths of planets in our solar system, HD 80606b follows a dramatically elongated orbit, swinging extremely close to its star at periastron and much farther away at apastron over its 111-day year. This unique path leads to violent swings in temperature and weather. As the planet approaches periastron, it is bombarded by intense stellar radiation, causing its atmosphere to heat by hundreds of degrees in just hours, a phenomenon unmatched in our solar system. This rapid heating is believed to trigger global, supersonic winds and planet-spanning storm systems. This inferno stands in stark contrast to the cooler, calmer conditions experienced at apastron. The severity of these changes is further shaped by the planet's rotation and axial tilt. If HD 80606b is tidally locked, the temperature difference between its permanent day and night sides would be immense. Even with rotation, the drastic and rapid heating and cooling from its eccentric orbit would still produce profound seasonal shifts. Astronomers study these dramatic changes using transit observations and radial velocity measurements. These methods provide data on the atmospheric dynamics and climatic effects of its elliptical orbit. The intense and rapid fluctuations in temperature and weather on HD 80606b create an environment that is exceptionally challenging for the development and sustenance of life as we know it. The rapid temperature increase as HD 80606b approaches periastron, heating its atmosphere by hundreds of degrees in mere hours, creates conditions far too harsh for life. The concept of habitability typically requires a stable environment where liquid water can persist on a planet's surface. However, the drastic swings on HD 80606b would prevent this. Any water would likely vaporize during the searing close approach and freeze solid at the orbit's distant, colder points. In a completely different extreme, the planets orbiting the pulsar PSRB 1257+12, located about 2,300 light-years away in Virgo, represent one of astronomy's most unexpected discoveries, challenging our understanding of where planets can form. Pulsars are rapidly spinning neutron stars that emit beams of radiation. As they rotate, these beams sweep across space like a lighthouse, producing a detectable pulsating signal from Earth. The discovery of planets around PSRB 1257+12 was groundbreaking because it proved for the first time that planets could form and persist in the violent aftermath of a supernova, in an environment utterly different from our solar system. What makes these worlds unique is not merely their existence around a pulsar, but the extraordinary conditions they endure, bathed in intense radiation from their dead star host. Pulsars are the super-dense remnants of massive stars that have exploded in supernovae, creating an environment of intense radiation and powerful magnetic fields that would be lethal to life as we know it. The very existence of planets in such a hostile setting raises profound questions about their origin and survival. Standard planet formation theories, which involve dust and gas coalescing in a disk around a young star, do not easily apply here, as a supernova should have obliterated or expelled any such primordial material. The planets orbiting PSRB 1257+12, discovered in the early 1990s, were a landmark find in exoplanetary science. These terrestrial mass bodies were detected through precise measurements of the pulsar's pulse timing. The gravitational tug of the orbiting planets causes the pulsar to wobble minutely, creating detectable variations in the rhythm of its pulses, a method uniquely suited to pulsar systems. The formation of these worlds is equally remarkable. One theory posits they are a second generation of planets, formed from a debris disk of material left over from the supernova explosion. Alternatively, they could be the surviving remnants of the original star system or captured interstellar bodies. The discovery of the PSRB 1257+12 system opened a new frontier in astronomy, proving that planets can emerge in or endure the most extreme environments imaginable. The conditions on the planets orbiting the pulsar PSRB 1257+12 are radically different from those in our solar system, presenting an environment that is almost incomparable. Planets in our system orbit a stable, main-sequence sun, which provides consistent light and heat, a foundation for the climate and potential life on Earth. In stark contrast, the worlds around PSRB 1257+12 orbit the super-dense remnant of a supernova, which bathes them in intense electromagnetic radiation and powerful magnetic fields. This pulsar radiation is far more violent than sunlight, capable of stripping away atmospheres, irradiating surfaces, and effectively sterilizing planets, rendering them inhospitable to life as we know it. While planets like Earth are shielded by their magnetic fields, the planets in the PSRB 1257+12 system are exposed to the pulsar's onslaught with little to no protection, suggesting they likely possess only a vestigial atmosphere, if any at all. The very mechanism of planet formation is also fundamentally different. Our solar system coalesced from a protoplanetary disk of gas and dust surrounding a young star. In contrast, the planets around PSRB 1257+12 may be second-generation worlds, forged from the debris of the cataclysmic supernova that created the pulsar itself. This suggests a second generation of planet formation, involving materials and processes vastly different from those that shaped our own solar system. The temperature conditions present another stark contrast. While planets in our solar system exhibit temperatures that allow for liquid water on Earth and ice in the outer regions, the worlds orbiting PSRB 1257+12 are likely subjected to extreme temperature swings, dictated by their distance from the pulsar and the intensity of its deadly emissions. These environments are far removed from the relatively stable and sun-warmed climates of our solar system. Shifting from stellar remnants to stellar interactions, Corot 2b, a hot Jupiter discovered by the Corot space mission, presents a fascinating case where a planet visibly affects its host star. Orbiting its star, Corot 2a, every 1.7 days, this gas giant's extreme proximity leads to significant and observable effects on the star itself. One of the most striking impacts is a powerful star-planet interaction. The immense gravitational pull of Corot 2b can stir activity in the star's outer layers, potentially leading to heightened magnetic phenomena, such as increased star spots and powerful flares. This dynamic relationship showcases the profound and mutual influence that can exist between a star and its orbiting planets. These effects are analogous to the Moon's influence on Earth's tides, but occurring on a far grander scale and involving magnetic fields and stellar plasma. Khorrat 2b's extreme proximity to its host star, Khorrat 2a, bathes it in intense stellar radiation, heating its atmosphere to the point where it expands and escapes into space. This escaping atmosphere forms a trailing cloud of material that interacts with the star. This interaction can transfer angular momentum from the planet to the star, potentially affecting the star's rotation rate and magnetic activity. Another fascinating aspect is the potential for the planet to induce chemical changes in the star. The atmospheric material bleeding from Khorrat 2b could accrete onto the star, subtly altering the chemical composition of its outer layers and its spectral signature. This process of accretion provides astronomers with a unique opportunity. By analyzing changes in the star's spectrum, they can infer the chemical composition of the planet's disintegrating atmosphere. Astronomers study these complex interactions using techniques like spectroscopy, which analyzes the star's light for chemical clues and changes in magnetic activity. Observations of the Khorrat 2 system significantly advance our understanding of how planets can actively influence their host stars, providing critical insights into planetary system evolution and the complex dynamics that govern them. The interaction between Khorrat 2b and its star, Khorrat 2a, illustrates a dynamic and reciprocal relationship, challenging the traditional view that stellar influence is a one-way process. These interactions demonstrate that planets, particularly close-orbiting hot Jupiters, can profoundly affect their stars by modulating magnetic activity, rotation rates, and even surface chemistry. The phenomenon of star-planet interaction, as seen in Khorrat 2, suggests that planets can induce magnetic disturbances, leading to increased stellar flares and spot activity. This implies that a planet's presence can directly shape its stellar environment, altering the very conditions under which both bodies evolve. In the case of Khorrat 2b, its extreme proximity and strong gravitational forces demonstrate how a planet's influence can extend beyond its own atmosphere to actively perturb its host star. This relationship also highlights the potential for severe atmospheric loss, as the planet is stripped of its outer layers by intense stellar radiation. The ensuing two-way exchange of material, where planetary atmosphere feeds into the star, further blurs the traditional boundaries between stellar and planetary domains. This material exchange can lead to changes in the chemical composition of a star's outer layers, providing astronomers with indirect methods to study the atmospheres of exoplanets by observing their host stars. The phenomenon of raining rubies on HAT P7b, an exoplanet located about 1,040 light-years away from Earth, is a captivating aspect of its atmospheric dynamics, driven by the extreme conditions present on this gas giant. HAT P7b is a type of exoplanet known as a hot Jupiter, due to its similar size to Jupiter, but much closer proximity to its host star, leading to significantly higher temperatures. The unique weather pattern, including the precipitation of materials like rubies and sapphires, is attributed to the presence of aluminum oxide in the planet's atmosphere. In Earth's conditions, aluminum oxide crystallizes to form corundum, the base mineral for gems such as rubies and sapphires, depending on the type of trace impurities it contains. The high temperatures on the day side of HAT P7b allow for the formation of aluminum oxide vapor within the atmosphere. The planet's close orbit around its host star subjects it to intense stellar radiation, heating the atmosphere to temperatures where metals can vaporize and complex chemical reactions can occur. As the vapor is carried by strong winds to the cooler night side of the planet, the drop in temperature allows the aluminum oxide to condense and form clouds. Further cooling may lead to the precipitation of corundum crystals, falling as rain in the planet's atmosphere. Depending on specific local conditions, such as the presence of trace elements like chromium or iron, These corundum crystals could theoretically resemble rubies and sapphires, hence the poetic description of it raining gems on Hat P7b. This extraordinary weather phenomenon is part of what makes studying exoplanets so fascinating, offering a glimpse into the vast range of environmental conditions that can exist beyond our solar system. The atmospheric dynamics of HATP-7b, including its potential for gemstone rain, are studied by analyzing the planet's brightness variations and spectral data. These observations reveal details about its temperature distribution and atmospheric composition, providing crucial insights into the complex chemistry and climatic processes on hot Jupiters. A similarly extraordinary phenomenon occurs on WASP-76b, an ultra-hot Jupiter located 640 light-years away in Pisces. This planet exhibits iron rain, a direct result of its extreme temperature differentials and unique atmospheric dynamics. Orbiting its star every 1.8 Earth days, WASP-76b is tidally locked, with one hemisphere permanently facing the star. This leads to dayside temperatures exceeding 2,400 degrees Celsius, 4,350 degrees Fahrenheit, hot enough to vaporize metals like iron. The mechanism involves powerful winds carrying vaporized iron from the scorching dayside to the much cooler nightside. There, the iron condenses into liquid droplets, forming clouds that precipitate as a rain of molten iron. This stark temperature contrast, driven by the efficiency of atmospheric circulation, creates the perfect conditions for this metallic weather cycle. Spectroscopic observations of WASP-76b have provided direct evidence supporting this remarkable phenomenon. Spectroscopy allows astronomers to detect the chemical signatures of elements in a planet's atmosphere by analyzing the starlight that filters through it. In the case of WASP-76b, the presence of iron vapor on the dayside and its absence on the night side provides strong evidence that the iron condenses and falls as rain before it can complete the circulation back to the dayside. In stark contrast to this hellish world, TOI 700D, discovered by NASA's TESS mission, has captured significant interest due to its potential for habitability. Located about 100 light-years away in the constellation Dorado, this exoplanet is the outermost world orbiting a small, cool M-dwarf star. The primary intrigue of TOI 700D stems from its position within its star's habitable zone, the region where conditions could allow for liquid water to exist on a planetary surface. Orbiting at a distance where it receives a similar amount of stellar energy as Earth does from the Sun, the planet's temperatures could, in theory, support liquid water, assuming it possesses a suitable atmosphere. Furthermore, TOI 700D is roughly Earth-sized, with a radius estimated to be about 1.2 times that of Earth, bolstering its profile as a promising candidate for a rocky, temperate world. This Earth-like size suggests TOI 700D is likely a rocky planet, similar to Earth or Venus. Planets of this type are more capable of retaining a stable atmosphere, which is another critical factor for habitability. A substantial atmosphere could provide essential gases and help regulate surface temperature via the greenhouse effect, preventing extreme temperature swings. Although TOI 700D is tidally locked, with one hemisphere in perpetual daylight and the other in endless night, this does not necessarily preclude habitability. A sufficiently thick atmosphere could effectively distribute heat from the dayside to the nightside, potentially creating a temperate zone where liquid water could persist. Furthermore, its host star, TOI 700, is a remarkably quiet M-dwarf with low stellar flare activity. Since intense flares can erode planetary atmospheres and bathe surfaces in harmful radiation, the star's calm nature significantly boosts TOI 700D's prospects for maintaining a stable, life-friendly environment. In stark contrast, LHS 3844b, an exoplanet orbiting a red dwarf star 48.6 light-years away, exhibits extreme temperature differences between its day and night sides. This is a direct result of its close orbit, and crucially, its apparent lack of a substantial atmosphere to redistribute heat. This terrestrial planet, LHS 3844b, completes an orbit in just 11 hours, placing it much closer to its star than Earth is to the Sun. This proximity results in intense stellar radiation on its day side, generating extremely high temperatures. The planet's tidally locked nature is the key factor behind its stark temperature contrast. One hemisphere is in perpetual daylight, while the other is in endless darkness. Critically, evidence from NASA's Spitzer Space Telescope suggests LHS 3844b has little to no atmosphere. Since an atmosphere is crucial for circulating heat, like Earth's does, the absence on LHS 3844b means heat is not redistributed. Consequently, the dayside temperature can reach approximately 800 degrees Celsius, 1,472 degrees Fahrenheit, while the night side remains drastically cooler. In contrast, Gliese 1214b is classified as a super-Earth, being larger than our planet, but smaller than ice giants like Neptune. With a mass about 6.5 times Earth's and a radius roughly 2.7 times larger, its size and mass suggest a composition distinct from the rocky planets in our inner solar system, potentially making it a water world or mini Neptune. This classification is significant because it suggests Gliese 1214b could possess a range of characteristics, from a dense atmosphere to a potential global ocean, depending on its exact composition. It is crucial to note that the term super-Earth refers only to its size, larger than Earth but smaller than Neptune, and does not imply the planet is Earth-like or habitable. Instead, it highlights the remarkable diversity of planets beyond our solar system. Super-Earths like Gliese 1214b are particularly intriguing to astronomers, as they represent a planetary class absent from our own solar system, offering unique insights into planetary formation, evolution, and the potential for life under vastly different conditions. Gliese 1214b orbits a red dwarf star about 48 light-years away in Ophiuchus. With an incredibly short orbital period of just 38 hours, it lies very close to its star, which profoundly influences its temperature and atmospheric properties. Observations indicate it possesses a thick, opaque atmosphere, potentially composed of water vapor or other heavy molecules. This has led to speculation that it could be a water world, with its surface possibly dominated by exotic, high-pressure forms of water. The study of Gliese 1214b and other super-Earths is vital for understanding planetary diversity. By analyzing their atmospheres with techniques like transit spectroscopy, scientists can decipher their chemical makeup, weather patterns, and ultimately, their capacity to support life. This research not only expands our knowledge of exoplanets, but also helps refine models of planetary system formation under a wide range of conditions. Proxima Centauri b, orbiting the closest star to the Sun, just 4.2 light-years away in the constellation Centaurus, stands as a prime candidate in the search for life due to several compelling factors. Its most critical attribute is its location within the habitable zone of its star, Proxima Centauri. Often called the Goldilocks zone, this is the region where temperatures could allow for liquid water, a fundamental ingredient for life as we know it, to exist on the surface, assuming the planet has a suitable atmosphere. Another promising factor is its Earth-like size. With a mass at least 1.17 times that of Earth, Proxima Centauri b is likely a rocky planet, similar in composition to our own world. This increases the possibility of Earth-like conditions and enhances its potential for habitability. Furthermore, its proximity to our solar system provides a unique advantage, making it a prime target for detailed observation and study with current and future telescopes. As the closest known exoplanet, Proxima Centauri b is a premier target for future missions and telescopes designed to study exoplanetary atmospheres, surface conditions, and potential biosignatures. Advanced instruments like the James Webb Space Telescope could analyze the chemical composition of its atmosphere, search for water vapor, and detect molecules that might indicate biological activity. However, significant challenges exist for its potential habitability. Its host star, Proxima Centauri, is an active red dwarf known for violent stellar flares and intense radiation. This activity could erode the planet's atmosphere and bombard its surface, meaning Proxima Centauri b would likely need a strong magnetic field to shield it and preserve any habitable conditions. Despite these challenges, Proxima Centauri b remains a cornerstone in the search for life. Its position in the habitable zone, its Earth-like size, and its proximity to our solar system make it a unique and compelling focal point for scientists aiming to find life beyond Earth. Shifting focus to another promising world, Kepler-22b, discovered by NASA's Kepler Space Telescope, has generated significant interest due to features that suggest it could support life. Located about 620 light-years away in Cygnus, this planet orbits within the habitable zone of its Sun-like star, Kepler-22. This placement is the primary reason for the scientific excitement, as it means the planet receives a similar amount of energy from its star as Earth does from the Sun, creating the potential for liquid water to exist on its surface, a fundamental requirement for life as we know it. Water could exist on its surface. The presence of liquid water is a cornerstone for life as we know it, essential for the biochemical reactions that sustain it. With a radius approximately 2.4 times that of Earth, Kepler-22b is classified as a super-Earth. While its exact mass and composition are still unknown, it could possess a rocky terrain or be a vast water world, entirely covered by a global ocean. The latter scenario presents fascinating possibilities for the evolution of aquatic ecosystems. The nature of its host star, Kepler-22, further supports its potential. This star is a G-type star, similar to our Sun, though slightly smaller and cooler. The relative stability and long lifespan of G-type stars are considered favorable for life, as they provide a steady and enduring source of energy for planetary systems. This relatively stable stellar environment, compared to the volatile flares of red dwarfs, enhances the possibility that Kepler-22b could maintain a stable atmosphere. However, its potential to support life depends not just on its location and star, but critically on its atmospheric composition, which is still a mystery. An ideal atmosphere would be thick enough to retain heat via a greenhouse effect, but not so dense as to cause a runaway greenhouse effect or create hostile surface pressures. Future observations with advanced telescopes like the James Webb Space Telescope may analyze the atmosphere of Kepler-22b, searching for gases that could hint at biological processes. In stark contrast, the exoplanet WASP-17b, discovered in 2009, defies convention with its bizarre traits, earning it the nickname, the backwards giant. Located about 1,000 light-years away in Scorpius, this gas giant is one of the largest known, with a radius nearly twice that of Jupiter, yet only half its mass. This gives it an extremely low density, akin to a celestial puffball. Most remarkably, WASP-17b has a retrograde orbit, meaning it orbits in the opposite direction to its host star's rotation, a rare and puzzling phenomenon that challenges standard theories of planet formation. The retrograde motion of WASP-17b poses a direct challenge to standard planetary formation models, which posit that planets form from a rotating disk and should orbit in the same direction as their stars spin. Its backward orbit implies a violent history, likely involving gravitational encounters with another massive body, such as a second planet or a passing star, that violently perturbed its path. This could have occurred through a sudden gravitational slingshot, or a slower, more complex process like Kozai cycles, which can dramatically alter a planet's orbital tilt. Another intriguing feature of WASP-17b is its atmosphere. Spectroscopic observations have detected water vapor and likely carbon monoxide. However, its vastly inflated size and low density create an exotic environment, where the intense stellar radiation likely drives extreme and unfamiliar weather patterns. Shifting focus from a low-density giant to a dense terrestrial world, we find Kepler-10b. Situated about 560 light-years away in Draco, this planet orbits its host star, Kepler-10, at an exceptionally close distance, completing a revolution in under 20 hours. This proximity subjects Kepler-10b to searing temperatures, earning it the nickname, the roasting rocky world. Its surface is likely a scorching landscape of molten lava, tidally locked in a permanent inferno.
The intense radiation from its host star heats the surface of Kepler-10b to more than 1,300 degrees Celsius, about 2,372 degrees Fahrenheit, a temperature that can melt iron and rock, creating a lava-covered landscape. This extreme heat makes Kepler-10b an unlikely candidate for hosting life as we know it, but it provides a unique laboratory for studying the compositions and atmospheres of rocky exoplanets, as well as the conditions under which they form and evolve. Kepler-10b's composition is primarily silicate rock, with a mass about 3.3 times that of Earth, and it has a radius 1.47 times larger than our planet's. These characteristics confirm its status as a terrestrial or rocky planet, similar in composition to Earth, Venus, Mars, and Mercury in our solar system. However, unlike the rocky planets orbiting our Sun, Kepler-10b's close orbit and the resulting high surface temperatures highlight the diversity of planetary environments that exist in the galaxy. The discovery of Kepler-10b was significant not only for confirming the existence of rocky exoplanets, but also for demonstrating the capabilities of the Kepler telescope and the transit method of detecting exoplanets. By monitoring the slight dimming of a star's light as a planet passes in front of it, astronomers can gather critical information about the planet's size, density, and orbital period. In the case of Kepler-10b, these observations have provided valuable data on the properties of rocky planets, including their densities, which in turn offer clues about their compositions and structures. Kepler-10b's extreme proximity to its host star also raises questions about its formation and history.
It is likely that the planet formed farther out in its solar system and migrated inward over time, a process that could have involved interactions with other planets or the protoplanetary disk from which it originated. Understanding these dynamic processes is crucial for piecing together the story of planetary systems, including our own. Gliese 436b, an exoplanet located about 33 light-years away in the constellation Leo, presents a paradoxical phenomenon that has intrigued astronomers since its discovery. Known as the burning ice planet, this world defies traditional expectations about planetary conditions and composition. Despite orbiting very close to its host star, Gliese 436, with a scorchingly short orbital period of just over 2 days, the planet is covered in what is known as hot ice, a state of water that exists under extreme pressure and high temperature. The surface temperature of Gliese 436b exceeds 400 degrees Celsius, 750 degrees Fahrenheit, conditions under which water would normally be expected to exist as steam. However, the immense gravitational pressure on Gliese 436b is so great that it forces the water into an exotic form of ice known as Ice X. This form of ice does not melt into liquid water at higher temperatures, but remains solid due to the pressure exerted upon it, creating a scenario where ice can exist in a stellar environment. This peculiar state of matter on Gliese 436b is a result of its unique atmospheric and physical characteristics. The planet's atmosphere is rich in hydrogen and helium, with traces of water vapor, which suggests that there is water present on the planet. However, due to the extreme conditions, this water does not exist in familiar states. Instead, the high temperatures and pressures transform it into hot ice and supercritical fluid, a state of matter that exhibits properties of both liquids and gases. The discovery of Gliese 436b has significantly expanded our understanding of the diversity of exoplanets and the range of conditions under which they can exist. It challenges preconceived notions about the behavior of water and the conditions necessary for different states of matter to form. The existence of hot ice on Gliese 436b suggests that there may be many more planets with similarly exotic conditions, defying easy categorization and expanding the possibilities for what conditions planets in the universe may exhibit. HD 209458b, also known as Osiris, stands out in the pantheon of exoplanets for its dramatic and visible process of evaporation. Located about 150 light-years away in the constellation Pegasus, this gas giant orbits its host star at a mere eighth of the distance that separates Earth from the Sun, leading to extremely high surface temperatures exceeding 1,000 degrees Celsius, about 1,832 degrees Fahrenheit. This close proximity to its star subjects HD 209458b to intense stellar radiation, causing its atmosphere to heat up and expand to the point where it starts to escape into space. The phenomenon of atmospheric escape on HD 209458b was among the first of its kind to be observed directly. Using the Hubble Space Telescope, astronomers detected hydrogen, carbon, and oxygen being blown off the planet at speeds of thousands of kilometers per hour, creating a vast tail of material trailing behind the planet, much like a comet. This escape process is so significant that it is estimated the planet may lose about 100 million to 500 million kilograms of mass per second. The evaporation of HD 209458b provides critical insights into the interactions between exoplanets and their host stars, particularly in cases where planets are located in close orbits. The intense radiation that drives the atmospheric escape on Osiris is also responsible for ionizing the escaping gases, which then interact with the star's light to produce the observable signatures that led to the detection of this phenomenon. Located about 200 light-years away in Cygnus, Kepler-16b presents a scene straight out of science fiction. Dubbed the Land of Two Suns, it was the first confirmed circumbinary planet, meaning it orbits both stars of a binary system. This unique arrangement allows for a spectacular double sunrise and sunset, mirroring iconic imagery from popular culture. NASA's Kepler Space Telescope discovered Kepler-16b using the transit method, which detects the faint dimming of starlight as a planet crosses in front of its host stars. These observations revealed its orbit around a closely bound pair of stars, one slightly smaller than our Sun, and the other a much smaller, cooler red dwarf. Roughly the size of Saturn, Kepler-16b is likely a gas giant, potentially with a rocky core. It completes an orbit in about 229 days, a distance that places it outside the system's habitable zone. Consequently, surface temperatures are likely too cold for liquid water. Despite this, its discovery remains profoundly significant, proving that complex and stable planetary systems can form around binary stars. The existence of Kepler-16b challenged previous assumptions, proving that planets can form and maintain stable orbits within the complex gravitational pull of a binary star system. This discovery has significantly broadened the search for exoplanets to include binary and multiple star systems, which are common throughout our galaxy. Furthermore, the study of Kepler-16b and other circumbinary planets helps scientists refine models of planetary formation and migration, revealing the incredible diversity of worlds in the cosmos. In a different part of the galaxy, the exoplanet GJ3470b, located about 100 light-years away in Cancer, has captivated scientists due to its rapidly escaping atmosphere. This Neptune-sized world, orbiting a red dwarf star, is classified as a warm Neptune. The phenomenon of its disintegrating atmosphere offers a rare chance to study atmospheric loss in real time, providing crucial insights into planetary evolution. Astronomers have directly observed this dramatic escape using the Hubble Space Telescope. The planet's close proximity to its star bathes it in intense ultraviolet and X-ray radiation. This energy heats the upper atmosphere to extreme temperatures, allowing hydrogen and other gases to reach escape velocity and stream into space. The rate of loss is staggering. GJ3470b is estimated to be losing mass up to 100 times faster than a comparable exoplanet, GJ436b, which is also known for its evaporating atmosphere. The rapid atmospheric loss of GJ3470b raises profound questions about its ultimate fate and the evolution of similar planets. Over billions of years, this continuous stripping could transform it from a gaseous world into a dense, rocky core, a potentially barren remnant of its former self, rendered inhospitable by its close orbit to an active red dwarf. This slow mutation offers a unique window into the dynamic life cycles of planetary systems and the varied end states planets can reach. In contrast, the exoplanet K218b, located about 124 light-years away in Leo, has captured the interest of astronomers and astrobiologists. Orbiting within the habitable zone of its star, K218, this super-Earth is larger and more massive than our planet, but smaller than the ice giants. What truly sets K2-18b apart is the landmark detection of water vapor in its atmosphere, a significant milestone in the search for habitable worlds. This discovery was made by the Hubble Space Telescope using transit spectroscopy. As the planet transits its host star, starlight filters through its atmospheric layers. By analyzing this light, scientists identified the spectral signature of water vapor, providing invaluable insight into the atmospheric composition and potential conditions on this distant world. K2-18b's orbit lies within its star's habitable zone, the region where temperatures could allow for liquid water on a planetary surface, given a suitable atmosphere. The detection of water vapor in its atmosphere is a promising sign, suggesting this potential could be realized. However, atmospheric water vapor does not guarantee liquid water on the surface or overall habitability. Critical factors like surface pressure, temperature range, and the planet's global climate determine whether liquid water can persist. The host star, K2-18, is a red dwarf, smaller, cooler, and more magnetically active than our Sun. This stellar activity can threaten planetary atmospheres with erosion. Despite this, K2-18b's specific conditions make it one of the most compelling targets in the search for habitable worlds. Future observations with advanced telescopes like the James Webb Space Telescope, JWST, will seek a more detailed atmospheric analysis, searching for other biosignature gases like nitrogen, oxygen, or methane. Shifting from a potentially temperate world to an inferno, WASP-121b intrigues astronomers with its extreme atmospheric properties. This exoplanet, located about 900 light-years away in the constellation Puppis, is an ultra-hot Jupiter. It is tidally locked to its star, with a day side so scorching that it tears apart water molecules and vaporizes heavy metals like iron and magnesium. Observations from the Hubble Space Telescope have even detected a stratosphere glowing with the light of evaporating elements, creating a truly alien and hostile environment. This planet is classified as an ultra-hot Jupiter, a gas giant more massive than Jupiter that orbits perilously close to its host star, resulting in searing temperatures. A defining characteristic of WASP-121b is the confirmed presence of a stratosphere, an atmospheric layer where temperature increases with altitude, much like Earth's. This discovery represents a major advancement in exoplanet atmospheric science. Observations from the Hubble Space Telescope confirmed this stratosphere by detecting how water molecules in the planet's atmosphere absorb stellar radiation, causing a significant temperature rise in the upper layers. This process, known as a temperature inversion, can heat the upper atmosphere to over 2,500 degrees Celsius, 4,532 degrees Fahrenheit, ranking WASP-121b among the hottest exoplanets ever analyzed. These ultra-hot conditions trigger exotic chemical reactions, including the breaking apart of water molecules and the existence of gaseous metals. The intense stellar radiation is so powerful that it strips away the planet's atmosphere, ejecting it into space to form a comet-like tail. These extreme conditions make WASP-121b a unique natural laboratory for studying the chemical and physical processes that dominate the atmospheres of the hottest exoplanets. The discovery of its stratosphere is particularly significant, as it helps scientists understand how stellar energy is absorbed and redistributed in the atmospheres of hot Jupiters. This knowledge is vital for building accurate models of atmospheric circulation and climate on distant worlds. As our journey to some of the most terrifying planets in the universe concludes, we are left with a profound appreciation for the cosmos's vastness and complexity. These distant worlds, with their extreme temperatures, violent atmospheres, and alien landscapes challenge our understanding of the universe and our place within it. Thanks for watching.